Okay, today we're going to learn a lesson on 3.5, which is the system of equations in three variables. And what we've learned so far basically is solving systems of two equations with two variables. And that might look familiar if you had like 2x plus 3y equals 4, and then negative 2x plus 4y equals 8 or something like that. And what we did is we did elimination, or we did substitution, or we even graphed to find the answers for x and y. Now we are going to do a system of equations that have three equations and three variables, which look quite a bit different, but there's a lot of similarities. An ordered pair is how we're going to answer what the solution is sometimes. For instance, the solution can be written in an ordered triple. And that is the solution of a system of three equations with three variables when they intersect at one point. Just 1 point. It's written usually like, in parentheses, the x value, the y value, and the z value. So the next question is, do all the rules change now that we're working in three variables? And what I was just saying a minute ago is no, there's lots of similarities between the two variables, the two equations and two variables. And there's one thing about it that's similar is there's only three types of outcomes. So your solutions can be one of three outcomes, and it's just like when we did two variables and two equations, in that those three outcomes would be like one solution, and that's what I was just telling you about the XYZ solution. Two, it could be infinite solutions. If you recall, that was one of our options. Or three, it could be no solution at all. No solution where all three of them intersect. And so when we did our two equations with two variables, we were looking at lines. We were looking at like a line that looks like this and a line that looks like this, and where it crossed right here, that was its solution. Or we saw parallel lines where there was no solution at all. Or we saw that there was one line that sat on top of another line, and this would be infinite. And so that is how we learned it with two equations and two variables. Three equations and three variables are a little more 3D. In that now we're not looking at lines, we're looking at planes. Like if you think of a piece of paper, that flat piece of paper is what a plane might look like. And so there's three individual planes intersecting at a specific point to get one solution. So if you notice right here, these three planes are going to intersect at one point. So its answer would be x, y, and z. The infinitely many solutions, let me take this on down. The infinitely many solutions are where the planes intersect in a line, and every coordinate on that line represents a solution of the system. The planes intersect in the same plane. Every equation is equivalent. every coordinate in the plane represents a solution of the system. So these are two different ways that it could be infinitely many solutions. And then there's one other way, one other situation that can happen, and that is that there's no solution at all. And that's where no points are in common in all the three planes. And so visually that's kind of what it looks like. That's not really what we'll be dealing with as much as we'll be dealing with equations. And we're going to be doing elimination. We're going to do substitution. And we're going to be trying to find our x, y, and z. That is the whole point of what we're doing. So when I look at this, this is a system of three equations. And if you notice, there's three variables. There's an x, there's a y, and there's a z. And we need to find the solution, if there is a solution to this. So what we're going to do in step one is we're going to use elimination. To eliminate a variable and thus make a system of equations in two variables. And then we're going to work on the two variables. So let's start by being wise about what to choose to eliminate. We could choose to eliminate some x's, we could choose to eliminate the y's, or we could choose to eliminate the z's. But let's look at what's easiest on us. And when I look at this, and it doesn't matter which one you choose, you just want to make it easy on yourself. So what I'm going to choose, the one that looks the best to me are the z's, because you kind of see some similarities with these three z's right here. There's small numbers, I like that. There's some positive and negative, I like that because that helps with elimination. So what I want to take is two of the equations, and I want to eliminate the z's out of the first two equations, let's say. So I'm going to use this equation and this equation, and I'm going to eliminate the z's. To do that, I'm going to have the same coefficient in front of the z. One of them will be positive and one will be negative, so it'll eliminate each other. And right now what I have is 2z in one of my equations and negative z in the other equation. So that second equation, I'm going to multiply by 2. And everything has to multiply by 2. So my first equation I'm going to leave alone. My second equation, I'm going to multiply everything by 2. And what I find myself with is two equations, and my z's are going to eliminate because 2z minus 2z is 0. And so I'm going to add, just like I did in first grade or something, vertically. I'm going to say 5x plus 4y is 9x, plus 3y plus 2y is 5y. My z's eliminate, and I get 2 plus 10, which is 12. Now I have one equation between my first and my second equations. Now I have only one equation with two variables. So what I want to do now is I've used the first two. So now I need to use that third equation, and I can use it with the first one or the second one. What I want to use it with is the second one, because I've got kind of the same thing going on with these two. My first equation is going to be, my second equation is 2x plus y minus z equals 5. And then the second one's x plus 4y plus 2z equals 16. So let's write those down up here, just to give me a better location, basically. And what I want to do is I want to leave my third equation alone, and my first equation I'm going to multiply by 2 again. When I multiply that first equation by 2, what I get is let me erase that. I'm going to get 4x, right? 4x plus 2y minus 2z equals 10. And so what I can do now, this equation times 2 is this one now. And I'm going to add like I did again in first grade and say 1x plus 4x is 5x plus 4y plus 2y is 6y. This eliminates and I get 26 when I add 16 and 10. So now I have two equations with two variables and I have finished step 1. So let's rewrite those. And I'm going to line them up nicely because I like to do that. I just think it makes it more organized. And so in step 2, we're going to solve the system of two equations. Okay, so you can see that I've already kind of decided what I want to do here. So I'm going to erase all this right now, and we're going to go back to that, but I'm having technical difficulties, so let's go back together. What I decided is to solve the system of two equations, I want to eliminate my y's. And to do that, the closest thing or the smallest thing that both 5 and 6 go into is 30. So I'm going to multiply the top by 6 and the bottom by 5, but not only 5 but negative 5, because I want to eliminate and they have to be opposite signs. So if I multiply everything by 6, each thing multiplies by 6 in this top equation. And then each thing will multiply by negative 5 in the bottom equation. So I get negative 25x minus 30y equals negative 130. So these eliminate, and 54 minus 25x is going to be 29x. Then 72 minus 130 is negative 58. Then I will divide both sides by 29, and I get x equals negative 2. And that gives me the x portion of my solution. After I find one of my variables, I want to take it back into the two equations and solve it for y. So I'm going to take this x back and put it into one of these. I kind of like this one because that x, that's just a smaller number in those equations. So I'm going to take my negative 2 for x, plug it into this equation, and when I do, I get negative 10 plus 6y equals 26. And then I'm going to add 10 on both sides, and I get 6y equals 36. And then if I divide by 6, I'm going to get y equals 6. And now I've got the y part of my solution. So the very last thing I'll do, and let's pull this back down, the very last thing I'm going to do is solve for the missing variable using one of the original equations with 3 variables. And so if I go back to one of the original equations, it doesn't matter which one I choose. So let's choose the one that seems the easiest maybe. And that's the very last one. I'm just choosing this one. I'm going to plug in my x value, which is negative 2, and my y value, which is 6, for each of those variables. And I'm solving this for z. So I've got negative 2 plus 24 plus 2z equals 16. This is going to give me 22 plus 2z equals 16. I'm going to subtract by 22, just trying to find out what z is. That will give me 2z equals negative 6, and last step is divide by 2, and so z equals negative 3. So I have x equals negative 2, y equals 6, and z equals negative 3. And that's my ordered triple.